Right. So today we are going to talk about LCM and GCD, which is least common multiple and greatest common divisor of a pair of numbers. It can be extended to more than two numbers, but we are going to focus on two numbers to begin with. And these are usually parts or smaller parts of bigger problems that you sometimes need to solve. So it's important to get these concepts clarified. I mean, these are not difficult concepts, but it's important to understand them thoroughly inside and out. So what is least common multiple? So given two numbers, least common multiple is exactly what it says. It is the least or the smallest number that is a multiple of both the numbers. So if I have numbers, let's say 5 and 6, then their least common multiple, the number that is a multiple of both 5 and 6 is 30. And there is no smaller number than 30 that is a multiple of both 5 and 6. You can check for yourself. The numbers are small enough. So that is the least common multiple. And what is the greatest common divisor? Again, as the name suggests, it is the greatest or the largest number that divides both the given numbers. So the least common multiple is the smallest possible number that is divisible by both, and the greatest common divisor is the greatest number that divides both of them. So that's how we proceed. And I'm going to talk about a general property of these numbers at the end. So let's first see what these calculations are, and then we will see what their general properties are. So let's talk about this. How do we find out LCM? LCM is least common multiple. So the first question is 15 and 25. Okay, so an important way to solve these problems is to find prime factorization. Prime factorization is a factorization of the given number in terms of the prime numbers. So the prime numbers are 2, 3, 5, 7, 11, and so on. And every number can be written as a product of prime numbers in a unique way. So what do we know? So we know 15 is equal to 3 times 5, and 25 is equal to 5 times 5, which is also equal to 5 square. I'm going to explicitly write it as 3 to the power 1 times 5 to the power 1, and this is equal to 5 square. So the way to find least common multiple is it has to do with this prime factorization. So what is the smallest? So suppose the number is x. Suppose x is equal to least common multiple of 15 and 25. What properties does x need to satisfy? X needs to be divisible by 15 and x needs to be divisible by 25. So if x has a prime factorization, let's say x is equal to some p1 raised to alpha 1, p2 raised to alpha 2, whatever, pn raised to alpha n, where pi's are primes and alpha i's are some numbers greater than 0, then this prime factorization has to have a number called 3, because if it is x is not divisible by 3, it will not be divisible by 15. So this 3 to the power 1 times 5 to the power 1 has to divide x. So we know clearly that so 3 is a member of the pi's and 5 is a member of the pi's, because prime numbers are not divisible by anything, and they are, you can think of these are the atoms that are building up the number. So 3 and 5 have to be the prime numbers. And what about their powers? So for this number to be divisible by 25, it has to be divisible by 25 is 5 square. So wherever there is let's say there is a 5 in this factorization, 5 to the power some alpha, this alpha has to be at least 2, because otherwise the number is only divisible by 5 and not 25, and the rest of the primes are not going to be divisible by 5, so they don't contribute to divisibility by 25. So we know that we know another condition now. So x has to be of the form 3 to the power something, let's call it a, 5 to the power b times maybe other primes, but it turns out that you will not need other primes because you are looking for the smallest number. So any number that you put here, 2 or 97 or any other prime you put here, is only going to make the number larger. So the powers of all other primes is 0. We know that a has to be greater than or equal to 1 because there is a 1 in the exponent here, and b has to be greater than or equal to 2 because there is a 2 in the exponent, and otherwise the number will not be divisible by 25. So x is a number of the form 3 times 3 to the power 1 times 5 to the power 2 times all other primes have power 0, which is basically 1. So x has to be equal to 3 times 25, which is 75. Therefore, we have the LCM of 15 and 25 is 75. So this is the least common multiple. What about GCD? GCD is the greatest common divisor. And again, we are going to use prime factorization. So now that we know this LCM, let's talk about GCD of 15 and 25, which is also denoted by just the bracket of 15 and 25. This is also a standard notation. This just a simple parenthesis and a comma separating two numbers stands for GCD. This is so commonly used that people sometimes drop the word GCD and just write 15,25 in a bracket. It's fine, that's a minor digression. So suppose y is the GCD of 15 and 25. Then y is again a number of the form p1 to the power alpha 1, p2 to the power alpha 2, pn to the power alpha n. For some, pi is the primes and some alpha is which are positive numbers. And I want the largest number alpha that satisfies these properties. So my number y has to divide 15 and y has to divide 25. This vertical bar means divides. This is standard notation. So y divides 15 and y divides 25. So what do I know? Y divides 3 to the power 1 times 5 to the power 1. And y divides 5 to the power 2. And I want the largest number that has these properties. So because it has to divide 5 square, which is 25, and it also has to divide 3 to the power 1 times 5 to the power 1, I have to take the smallest possible exponent of each prime, so that's the only way I can satisfy this. So suppose, for example, it had been, let's say, 3 to the power, so suppose y has to divide 3 to the power 5 times 5 to the power 9, and y has to divide 3 to the power 6 times 5 to the power 10. Then the smaller exponent, maybe let's not have it 10, let's have it 8 here. Then the only way I can have the largest number here is 3, y is equal to 3 to the power 5 times 5 to the power 8, which is the smaller of each prime's exponent that I'm combining here. And that's what is GCD, the greatest common divisor. So I know that so y divides 3 to the power 0 times 5 to the power 2, and y divides 3 to the power 1 times 5 to the power 2, or rather 5 to the power 1. So y has to be equal to 3 to the power 0 times 5 to the power 1, because that's the only way it can divide both the numbers and be largest such number, which is 3 to the power 0 is 1 times 5, which is just 5. So we know that GCD of 15 and 25 is 5. So the general rule that we came up with is, I'm going to state that rule because this is going to be useful for other problems as well. So suppose I'm given two numbers. Let's say a is a number that is p1 to the power alpha 1, p2 to the power alpha 2, pn to the power alpha n, and p is a number, the same primes are not changing, p1 to the power beta 1, p2 to the power beta 2, pn to the power beta n, where alpha is greater than or equal to 0, beta is greater than or equal to 0, but they are not both equal to 0, otherwise I can just drop that prime from the factorization. So then LCM of a and b is equal to p1 to the power max of alpha 1 beta 1 times p2 to the power max of alpha 2 beta 2 and so on, pn to the power max of alpha n beta n. That's how we can find that's how we can use prime factorization to find the LCM. And similarly, GCD of a and b will be equal to p1 to the power min of alpha 1 beta 1, p2 to the power min of alpha 2 beta 2, and all the way to pn to the power min of alpha and beta n. So we are using prime factorization and uniqueness of prime factorization to solve these and many other problems succinctly. And now that once we know this theory and now that once we know the math, so let's talk about other numbers. So the second one is 3 and 14, right? But I think now the machinery should be fairly straightforward. So second is LCM of 3 and 14. As always, given such GCM or rather GCD or LCM type problems, always find prime factorization. So 3 itself is a prime. 3 is 3 to the power 1. And 14 is equal to 2 to the power 1 times 7 to the power 1. So LCM of 3 and 14, again take common primes and take the largest power, is equal to 2 to the power 1, 3 to the power 1, 7 to the power 1, which is 42. And GCD of 3 and 14 is equal to, now take the common primes basically and take the least power. So this is 2 to the power 0, 3 to the power 1, 7 to the power 0, and this is equal to 2 to the power 1, 3 to the power 0, 7 to the power 1. So there are no common prime factors, or the prime factor, the only common factor is 1. Or another way of looking at it is, so if we go through the math, it will be 2 to the power min of 1 and 0, which is 0. Similarly, 3 to the power min of 1 and 0, 7 to the power min of 1 and 0, which is 1 times 1 times 1, which is 1. So the GCD of these numbers is 1. Let's go through the math again. 10 and 35. Now the pattern is becoming clear. So let's see GCD of 10 and 35. Again, let's find prime factorization. 10 is equal to 2 times 5. 35 is equal to 5 times 7. For GCD is equal to 2 to the power 0, 5 to the power 1, 7 to the power 0, which is 5. And LCM is equal to again 2 to the power 1, 5 to the power 1, 7 to the power 1. What do we have here? It is 1070. So LCM of the two numbers is 70 and GCD is 5. One thing I want to mention, and we can also prove it more rigorously, is note that the product of two numbers is equal to the product of their GCD and LCM. Try to prove it yourself. I think you have enough machinery here. The prime factorization, the uniqueness of prime factorization, and the way we are using min and max. You can easily or not so easily, you can show that the product of two prime numbers, product of two numbers is equal to the product of their LCM and the GCD. So it's a good sanity check. So 35 times 10 is 350, and GCD times LCM is also 5 times 70 is also 350. So this is an important theorem. Let's just state it. Product of two numbers. This is true for any two numbers. Of course, positive integers is equal to LCM times GCD. Try to prove it. So we can discuss it maybe in brief next time, but this is an important property that we should not forget. So the fourth one is 12 and 18. Let's go through the steps here. GCD of 12 and 18. So again, 12 prime factorization is, now this is 2 times 9 is 3 times 3. 18, oh what is that? I think 2 times 2 times 3 here. 18 is 2 times 3 times 3, sorry. So 12 is equal to 2 square times 3 to the power 1. 18 is equal to 2 to the power 1 times 3 square. So GCD should be, as you already know, this is going to be 2 times 3, which is 6. LCM is going to be, now let's use our theorem, is going to be 18 times 12 divided by 6, which is 36. So this is another way of solving, and this is also a sanity check, as well as this is a clean way of solving stuff, because there are very fast algorithms. I mean, we can talk about it later, but there are super fast algorithms that don't require you to find the prime factorization to calculate the GCD. there are fast ways of doing this, because prime factorization can be tedious. If you are given a very large number, then finding prime factorization is difficult, but finding GCD is not difficult. Prime factorization is one way of finding GCD, but there are other faster ways of doing it. And once you know the GCD, is finding LCM is straightforward because of this our theorem. Product of two numbers is the product of LCM and GCD. So that's about it. Try to prove this important theorem, and then we can discuss it at next time. Thank you.